All right. Welcome everyone to the CHASC seminar talk discussion. I don't have to remind you that this is a very sort of informal type of thing. So you're welcome to interrupt at any time. If you're feeling shy, just put your hand up and I'll call on you. But don't be shy. Feel free to interrupt any time. The speaker today is Colin Burke. He's from Yale. He's been working with Priya Natarajan at Yale. He's been working on black holes, and he's also been interested in working on preparing for the LSST data deluge. So that is also something that you might want to talk to him about. So, and today he's going to be talking about black hole, a population study of black holes, using a very complex hierarchical Bayesian model. And he's keen to receive feedback.
Yes.
Or so I have told him. So we'll see.
Yes.
So take it away, Colin.
Fantastic. Thank you very much for having me. Yeah, really excited to get to talk to an interdisciplinary audience. So feel free to interrupt if you have any questions. I'll try to keep it. Oh yeah, minimize this. At least.
Yeah, that should be.
That's good enough. Okay. Yeah. All right. So we'll get right into it. So just to motivate this from the perspective of, the science question. Oh, it is cutting off a bit, but it's fine. So the motivation for this work kind of stems from two observations. That's how I think of it. One is observations of very massive black holes at very high redshift. So when the universe was only several 100 million years old. And it's very hard to grow a supermassive black hole that quickly from standard Eddington limited accretion. And it used to be we had supermassive black holes with masses like 10 to the 9 at like redshift 6 and 4, and now it's like with JWST, it's like redshift 10, 11. So the problem has only gotten worse. And then there's these observations in the nearby universe that we've known for the past few decades, actually, like with since HST launched with the Nuker team, that massive elliptical galaxies, pretty much every massive elliptical galaxy, we think, harbors a supermassive black hole in its center. And so understanding the demographics and the populations of black holes and galaxies across cosmic time is very interesting. And in order to solve this problem, I mentioned at the beginning of how do we get these very massive objects, very quickly, very early on in the history of the universe, theorists have proposed different mechanisms for how you can form a seed black hole, which would have, depending on what mechanism is your preferred mechanism, they can be broadly classified into what we call light or heavy seeds. And so light seeds would be like remnants of very massive population 3 stars. And so when those explode, you might get a black hole remnant of, maybe 100 solar masses. And the other category that people like to talk about is direct collapse. So under very specific conditions, low metallicity, everything, you can maybe directly collapse structures at high redshift. And those can form more massive black holes, maybe 10 to the 4 solar masses. And that would be much easier. You don't have to grow as much if you're already at 1,000 solar masses. You don't have to grow as much as you would if you were, 10 or 100 solar masses. And so what happens is when you get to low redshift, so the modern day present universe, the most massive black holes and massive galaxies have grown a lot from this accretion, right? And from mergers also. And they've and from, black hole feedback with the host galaxy, and this kind of erases the signature of seeding. So it's hard to infer a lot from them. But some modeling has shown that the fraction of low mass galaxies, which have intermediate mass black holes, so from, say 100 to 1,000 solar masses, The fraction of galaxies that have these black holes or not is sensitive to the initial seeding mass function. Okay, and so this is an interesting observational constraint, at least. So, yeah.
So is the gap from like 1,000,000 to 100 million solar masses is in the black hole masses? Is that real or is just an observational artifact or?
Oh, you mean the gap here?
Yeah.
I think that's just the figure. Yeah, just to simplify the figure. Yeah, we know of black holes that are in this mass range, but below 10 to the 5, the evidence is less clear. Yeah. Yeah.
But there's no obvious.
There's no sharp boundary, I would say. Yeah, no obvious boundary. And yeah, it's just, we can only find these at high redshift just because of our limited sensitivity, right? But we know of many 10 to the 6 to 10 to the 7 solar mass black holes in nearby Seyfert galaxies. Yeah, those tend to have lower mass black holes in them. Yeah. Good question. Okay, so this kind of sets the landscape and yeah. So already said that. Can't read it anyway, and this is not meant for you to read, just to convince you that a lot of theory papers have been written to propose these different mechanisms. So this is a very hot topic. Well, it's been a hot topic for a while and is now with JWST. And so, yeah. And so just to go back to the, what's the previous kind of observational work that's been done before. So this is work from Elena Gallo and collaborators. And so what they did is they conducted this really nice survey with the Chandra X-ray Observatory called the AMUSE survey. And it was a volume limited survey, and there was a field, that they pointed to with field galaxies, and there was a cluster as well that they did. And this is the results for, I think, the field galaxies. And they've got these constraints here, which I'll talk about in a second, how they get this on. So this is the occupation fraction on the y-axis and the stellar mass of the host galaxy on the x-axis, right? And anywhere to the left of this gray shaded line is allowed by the data. So we know in very massive galaxies that the fraction of those that host supermassive black holes is of order unity. But at lower masses, below 10 to the 9-ish, it's much more uncertain. And I'll talk about how they get these constraints in a second. But also to draw your attention to these blue squares, those are predictions from semi-analytic models, which basically, you can track black hole growth from accretion, prescription, and mergers using these merger trees from cosmological simulations. And this is work from Angelo Ricarte, who's a BHI fellow here. And what he's shown is that, this is showing for the heavy seed model, but you can make predictions based on the efficiency of seeding, black hole seeding at high redshift, what the redshift 0 occupation fraction should be. And at least some of their models for the heavy seeding are consistent with these observational constraints.
Another silly question.
Yeah, please.
What exactly does occupation fraction mean? I mean, for instance, if there is a 1,000,000 mass galaxy, then there's a 40% chance that it has a black hole. So.
Yeah. We can't say for sure whether it has a black hole, but on average, 40% would have a black hole. That's right. Yeah. And we know, like, there may be, even in massive galaxies, there may be outliers that don't have a black hole. So it's kind of a rough metric. Yeah. But it's simple, and that makes it useful, I think. Yeah. Okay, great. And so this is a similar plot showing other observational constraints from dynamical signatures and mission line ratios. I won't really get into this, but many people have tried different techniques to measure this occupation fraction. And these colored point lines here are predictions from various cosmological simulations. And as you can see, they're kind of all over the place. So this is, again, more motivation for why we want observational constraints on this. So this is all redshift 0, by the way.
Why at the right-hand side, why did the error bar increase? Is
Uh,
it just because you have fewer, mass black holes?
Yeah, I think so. That's, limited by the volume of the simulation that they've looked at, probably. Yeah, not having enough numbers of very massive galaxies to get smaller error bars than that. Yeah. All right, good. Okay, so how can we actually, measure or try to model in a Bayesian way whether a galaxy has a black hole in it or not? Well, forget about black holes for a second, and I'd like to introduce you to something called logistic regression. So who's heard of logistic regression before? Yeah. Okay, about half, good. So take this example. Say you want to predict what's the chance on any given day it will be a sunny day or a rainy day as a function of, say, temperature outside. Well, you can model this probability distribution using a sigmoid or a logistic function, where you have this probability distribution here, which depends on some variable z, which could be the temperature in this case, or it could be some more complicated formula, hierarchical formula that depends on many other parameters. So temperature, latitude, whatever else, whatever altitude you're at, whatever else, right? And then you can write down a Bernoulli likelihood. Okay, it's barely there. On Zoom, it looks okay, but it's a bit cut off on the projector, but it's barely there. So you can write down the standard. This is just a Bernoulli likelihood function, okay? Where y here is either 0 or 1, depending on the outcome of this probability function. And so that's a way you can quantitatively model the number of sunny days or rainy days throughout the year. Okay. And so what we want to do is something similar. We want to model what's the chance that you would have a black hole or not in your galaxy as a function of this occupation probability, which is a very similar problem. Okay, so now let's go to the data that we have. So let's say you have a plot here of X-ray luminosity, log of X-ray luminosity, against log of stellar mass of the host galaxy. And this is again from the AMUSE survey, from the previous work. And in a nice, volume limited survey, you kind of have a known luminosity threshold. So that makes the interpretation a bit easier. So it's easier to start with this figure. And what you can do is you can fit a line to this data and then add this logistic component into the probability distribution. So it's not exactly like pure logistic regression, but it's sort of in there. Sometimes these are called Bayesian hurdle models because you have to, the idea is in order to observe a luminosity from a black hole, there has to be a black hole there in the first place, right? Obviously. But there's some probability that there's no black hole there and the luminosity you get would be 0, which would not appear on this figure, but you need to incorporate that into your likelihood function. And so these are called hurdle models because the idea is you have to get past this initial hurdle of having a black hole in there in order to observe it. So these similar kind of models come up a lot and have many applications. Survival analysis and medicine and things, to give you one example. But we have a more complicated maybe problem in astronomy, not unique to astronomy, where we have data censoring, right? So we have some limited sensitivity of Chandra, and below a certain luminosity, we don't know if there's a black hole there or not, right? Or maybe there's a black hole there, but it's just not luminous enough to be detected in our survey. Okay, for these points here where we have detections, you can assume there's a black hole there if you know that luminosity that you're seeing is coming from the black hole. But for these limits, we don't know. And so how to model this? So it's kind of simple. So you just, the probability distribution of a certain X-ray luminosity given the stellar mass can be modeled with a Bernoulli likelihood, a Bernoulli probability distribution, times the Eddington ratio distribution function, okay, so which has this horrible acronym EARTH. And you can think of this as the scatter on the plot. So if there is a black hole, this Bernoulli thing is equal to 1, and then you are somewhere on this plot, right? If there's no black hole there, and this depends on the occupation probability, then this Bernoulli thing is equal to 0, and your luminosity is 0. Okay, and it turns out we know actually pretty well what the Earth or what the scatter on this plot looks like. You can ask me about that later, or now, if you're curious. And you know, it's not as easy as censored linear regression with normally distributed scatter. It's actually a smoothly broken power law scatter. Okay, and so basically you have to define this Eddington ratio function, so then which tells you how bright you'd expect these black holes to be as a function of stellar mass using these tools. Yeah.
So why is there a convolution with the normal?
Because you have uncertainty on the stellar masses and the luminosity. So it smooths out the, and
But that's good, that's more of a data driven thing, right?
Yes.
And it's not an intrinsic.
well, if you convolve it, then you can back out the intrinsic component if you know what
Then
you've
you-
convolved it with.
You would have to change the normal for every survey differently.
Potentially, yeah. It's also blurred out what I should have said. It's also blurred out by the fact that at a given stellar mass, here I'm using stellar mass as a proxy for black hole mass because we don't have black hole masses, right? At a given stellar mass, there's a kind of an expected value for what the black hole mass would be, because there's a correlation between the two, but there's some scatter in that correlation, right? And there's some uncertainty associated with what the slope of the correlation is and that kind of thing. So that's also folded into this, yeah.
So the normal effectively models the scatter.
Yes. Great. Great, yeah, and so if you make these kind of simple assumptions,
Sorry. one more.
yeah, please, no, this is
So
great, yeah.
The normal models the scatter and log luminosity.
Yeah,
Or
correct.
log mass rather than mass. itself.
Yeah, correct. Everything's logged, yeah. Yeah, here I've written it in luminosity space just because I think it makes it a bit easier, but yeah, Okay. All right, so there's another term here, which is the probability that any of these detections is not due to like something other than a black hole, at least not the black holes that we care about, like say a low mass X-ray binary or something that wouldn't count, but it's not what I care about. So there's a mixture of possible sources that we tried to account for in this because we kind of roughly know, again, there's a relation between the luminosity you expect from like a low mass X-ray binary and the either star formation rate or stellar mass of the host galaxy. So we tried to fold that into the model as well. Of course, it's good to always double check with other observations to try to rule that out. Okay. But that is a problem to consider, especially for future X-ray missions. And then kind of underappreciated fact in astronomy, at least, is that when you have limits, you can integrate, essentially marginalize your likelihood over all of the non-detections. So in this case, we integrate this. It's horrible. This smoothly broken power law Eddington ratio distribution function multiplied by this Bernoulli thing. You integrate that from your upper limit on luminosity to minus infinity. And that takes into account the fact that you might have some black holes that have zero luminosity because there's no black hole there, or there is a black hole there, but it's just not luminous enough to be detected. That can all be accounted for by, if you've got the right likelihood, you just integrate over the unobserved space. And then you can back out this P occupation, the occupation probability, or occupation fraction, which it is a probability, it's a, and so that's what I've shown in blue, and in this case, it's just a limit, right? So anywhere within the blue space is allowed by the data. So the occupation fraction could be 1 everywhere. We don't know, because we're basically getting this consistent number of detections as we step down in stellar mass, and a consistent scatter, given the limits here, if that makes sense. So it's consistent with full occupation, but we can still put a useful limit on this, okay? And so you can make like a 1 and 2 sigma limit here, which I've done in the different shades here of blue, and then compare that to the previous work from Miller 2015 on this data set. And they didn't quite have the right scatter. They just did, what they did was closer to like pure linear regression with normal scatter. In this case, it didn't matter too much, okay? Okay, good.
So what these shaded regions are telling you are basically the lower bounds on the lower limits on the occupation.
Exactly right. Yeah, exactly right. Yep. Yeah, it's like a credible interval on the occupation fraction. Yep. Yep. Okay. And so so what we're inferring is this occupation fraction, which we model using a logistic type function, and I'm happy to talk about the motivation for that. But we chose a very flexible function just because, that can model all the reasonable possibilities, okay? And so this lets you back out the occupation probability, even though the actual detections here show that the error bars are much lower than what you can infer. Okay, so now let's take a step further. And this is much less convincing to the eye, but once you've written down this Bayesian model, it's exactly identical problem. Because you've considered the upper limits consistently, you can apply this now from a volume limited survey to a flux limited survey, just by, again, integrating under all of those limits. There's no difference. At least the way you treat like a luminosity limited sample versus a flux limited sample could be a bit different depending on how you've implemented your selection function. But if you use all of the upper limits, which we have been very nicely tabulated in the Chandra source catalog, and you integrate under of those, you kind of avoid having to think about the selection function too much because they've already done it for us, right? Okay. And so again, this looks much less convincing to the eye, but I would argue it's conceptually identical problem. And we're using all the data now. So it's not a surprise that the occupation fraction constraints are much better compared to the Muse survey. In this case, we're able to get roughly order of magnitude improved constraints on the occupation fraction. And you can see that there are many detections, even around 10 to the 9, maybe 10 to the 8 stellar masses. And so that's consistent with a relatively high occupation probability at that stellar mass.
So
Yes.
I'm not sure if I understand this, the right-hand figure.
Okay.
The X-ray detection fraction.
Mm-hmm.
Why is that so much outside the allowed range?
Yes. So the detected fraction has nothing to do, well, it has something to do with the occupation fraction that you infer, but because most sources that have a black hole in it aren't actually accreting enough to be detected, the overall fraction goes down
But
that you observe. But what you infer using this model can be quite different from what you actually see.
But wouldn't you expect that as mass increases, then the chances of.
Oh, okay. Yeah, then you would have, yes. So that you can see a bit more clearly from the AMUSE survey, where at 10 to the 10, the fraction is close to 1. And you could imagine that had they gone a little bit deeper, maybe it would have been equal to 1. Yes, good. So one thing I left out, yeah, why isn't that the case here? Because Chandra has not observed, most galaxies. And a lot of galaxies that I included here, for this particular figure, I combined Chandra, XMM, E Rosetta, and Rosat, which is very shallow. So I think that's why, is because a lot of these galaxies just have Rosat limits, which are not, very constraining. It would be very unlikely that you get enough luminosity out of an AGN to be detected with Rosat. Only the very nearby, rapidly accreting black holes would be detected with Rosat.
So from this sample, is it possible to convert it into, or take a subset that's volume limited and see if it recovers similar results to AMUSE?
Interesting idea. Yeah, I haven't tried that. Yeah, that's an interesting idea. Yeah, you could apply some cuts and see. Yeah, that's a good idea. I haven't done that, but yeah, the way I tested it was with like some mock data and make sure, okay, you can actually convince yourself, given the assumptions and the likelihood, right, that we can recover the occupation fraction. So that's one thing I did, but yeah, that would be a great test to do. Yeah.
So I guess a similar question is, if you weren't selecting on all of these combined data sets, if you had limits from fewer of them, then how would your distributions, the ones that are blue, change?
Say you had say you only did it with Rosat, which is a very less sensitive survey than Chandra, but they looked at all sky. Yes, the inferred occupation fraction, it would still be a lower limit, but it would probably be moved here to like 10 to the 9. Because you're not detecting as many things, because as you go down to lower masses, the luminosity decreases because the black hole mass decreases. And so that's what these constant lines here are showing, is if you had a black hole with the same accretion rate, so the amount of material coming into the black hole is the same, but because the black hole mass is, lower, the luminosity that you get out of it is also lower. So yes, you need a lot of sensitivity to detect things at low stellar masses, if that makes sense. So it should be consistent, but the limits will be less good, less constraining, with a worse survey. Also, another thing I didn't mention, Chandra preferentially observes things with black holes in it, right? You're not gonna go out and write a proposal to stare at a random galaxy. You might, but yes, so that is why we have to include, whether it's a detection or not, doesn't matter. But your likelihood will be, your inference will be biased if you only use Chandra. So we had to include either limits or detections for every galaxy within the volume that we considered to try to mitigate this effect. Hey, anything else? Anything on Zoom?
Where do you get your, for the upper limits, where do you get your catalog data from?
So from Chandra, it's they really give it to you. You put in the coordinates and they spit out an upper limit based on.
How do you know where to look? Is that where do you get the catalog of AGNs?
Okay, yeah. So like for the Rosat and E Rosetta, it's a bit more sketchy. So you just look at like the catalog of like 5 sigma detections that they published. Like I forget what the name of the Rosat one is, RS, something like that. And if there's no detection in Chandra, but Chandra didn't observe it. Same for these other ones.
So it's
then you use the Rosat sensitivity to estimate.
So when you say flux limited, not only is it, it's flux limited different layers.
Yes, yes,
I mean, even in the same
Yes.
pointing, you can have multiple flux limits.
yes. And I tried to use, in that case, I used the strictest one to try to get the most information out of it. But yeah, this is why using the upper limits for every point, you know, in this case, is the way to go, rather than trying to model like a selection function as a function of like flux and stuff, and then trying to integrate that and multiply that by your likelihood. Like you can do it that way, but it's, in this case, it's easier. Yeah. It is more computationally intensive because you have to do this integral over many, many points. But it's not that bad. But for LSST, it might be a problem.
Oh,
Yeah. So.
well, at least you know exactly.
So, okay, great. Yeah. Anyway. Okay, so these are the simulations I was telling you about earlier, where you say, okay, let's assume a luminosity or limited like sample and some mock data. Can we recover the true occupation fraction, which is this y equals x line? And you can up until a certain point, when you only get a limit because you've saturated beneath your sensitivity. And on the right is showing that this parameter, delta, which is basically the slope of the luminosity function. So the slope of this power law scatter, essentially. So you have to jointly infer, right, the scatter and this occupation probability together. Okay, and skip this, but we tried to check, whether these sources are consistent with X-ray binaries and stuff. And so here's our recovered luminosity function, which again comes from fitting the scatter to that scatter plot. It's crazy how much information there is in a simple scatter plot like this, right? Now, one thing is we do not have any information in our likelihood about the normalization of this function in volume, because it's just a fraction thing, the way we've written. So we did renormalize it but we know, from other observations. So we just renormalize it to, what we care about is whether this is what this looks like at low luminosities. And you can infer this, and our inference is shown in blue, and compare this to previous work at redshift 0, which is shown in the purple. And what we found is that it's consistent with the previous work. Maybe not, not that surprising. We've assumed the same parameterization, but we have left the slope of this, could be very different potentially, depending on our data. We found it's consistent with an extrapolation of this low luminosity X-ray luminosity function, several orders of magnitude lower than what's been previously observed. So I thought that was quite cool. And this is other work from Andrea Sacchi. Is it Sacchi? Sacchi. Apologies, from Andrea Sacchi, who did a similar study constraining the low end of the luminosity function from E Rosetta. And again, consistent with the power law extrapolation to very low luminosity. So we think this indicates that it's AGNs all the way down. The more sensitive you are, you should be able to detect lower luminosity things. Is there a
question?
Yes, please.
Yeah, on your previous slide, you showed an extrapolation that goes down to 10 to the 37 ergs per second. You're starting to get into X-ray binary range at that point. So I'm just wondering about the confusion.
Yeah, exactly. Great question. So yeah, it is a problem. So what we tried to do is we tried to model, okay, what's the chance that a 10 to the 37 luminosity detection comes from an X-ray binary or like a very low accreting AGN. And so we used the relationship from Brandon Lamer's papers, which he has a nice correlation of like the expected X-ray luminosity that you would get from X-ray binaries in a given galaxy as a function of the stellar mass and star formation rate of the galaxies. And since these are all low mass galaxies, nearby galaxies, we have like reasonable estimates for those quantities. And then you can do something quantitative. Like I said, more detailed observations would be needed to, I think, say something definitive. But we tried to incorporate it in a statistical way using these relations. So does that answer your question?
Yeah, sort of. So you're relying on on some knowledge of essentially the ability to produce massive stars, or the number density of massive stars that would be produced in a dwarf galaxy that would then turn into X-ray binaries.
Exactly right, yes. And yes, in reality, all of these galaxies probably have their own distributions of X-ray binaries in them. And you could model that and try to infer it. We didn't go quite that far, but we took a step in that direction. Yeah. There's another thing that helps us a bit, which is the fact that a lot of these galaxies, because they're so nearby, I don't know if I mentioned this catalog that we use is like, it only goes out to 50 megaparsecs. So a lot of these galaxies are quite extended. And you know, even a 1x arcsecond aperture in the center of the galaxy, you know, if you assume, you know, you have this relation from this Brandon Lamer's papers about the X-ray luminosity that you would expect from the entire galaxy, right? And if you assume that the X-ray binary distribution in a galaxy roughly follows the light profile, then it's even less likely that you would get that much luminosity within just the center of the galaxy. So you can try to do a rough calculation from that as well. So that helps us a bit. But when you go to further distances, like with Axis will do, this is going to be a problem because, you know, a 1 arcsecond aperture is now covering your entire galaxy. Yeah.
Question about this figure.
Mhm.
So your purple boxes there,
Mhm.
they seem to follow the new model rather than the old model better.
Yeah.
So
Yeah, good question. Yeah, I can't remember exactly how they fit this broken power law in the dashed line, but I know they did it in several redshift bins and maybe, you know, trying to constrain that. So that could be why this may not be a pure fit to only this data. Yeah, but I have to check on that. Yeah, and there is a bit of an outlier here, which I don't know why. Could be dragging that slope down a bit. Yeah, so
it's the one with the largest error bar.
yeah,
Seems like it should have the least effect.
yeah, true. Yeah, I don't know. Yeah. All right. Yeah, I was happy enough with with this agreement that I left it there. Yeah. Yeah. No. Yeah.
X-ray luminosity, what you are saying, majorly is coming from AGL, right? Like, is it
Yes.
X-ray binaries contributions?
Not included here. So yeah. So because in our likelihood, again, I didn't show like the X-ray binary term that's in there, but it's basically a mixture model. So for every detection, it will try to assign some probability that that detection is described by this power law or the X-ray binary power law. And with,
Approximately, like, how much percentage of is coming from X-ray
Oh.
binaries?
I found with this data set, again, if you go to larger volumes or whatever, this could change. These square points here, I found were more likely to be coming from X-ray binary, is assigned a higher probability of that for those 2 points there. One of them is, of course, very low. So that will not contribute much to the occupation fraction or the luminosity function. Yeah.
Whatever X-ray we are getting is very likely that coming from AGL itself.
Yes, according to the model that I've written down, which again, more observations should be, yeah, done to confirm this, but yes. Yeah, it's nice to do it in a quantitative, probabilistic way, at least. To try to. And then, yeah, go out and do some observations with this prior information, see if we update that prior in our model. All right, good. Okay, so I went out and did kind of the same thing in other surveys. So I thought, well, you know, black holes also produce radio emissions. So I looked at the VLA all sky survey. In this case, we don't have to worry about like bias from targeting certain observations. And we found a consistent result, also a limit, not as constraining as the X-ray data was, but at least it's consistent. So that was nice. And you can also constrain the radioluminosity function. In this case, the VLA survey that I used is not super deep, so our constraint wasn't that much better than what's been done already in the past from Mouch and Sadler's 2007 paper. But at least it's consistent with the luminosity that you'd expect in the radio. And I should also mention we assume priors from these luminosity functions. So if the data is not good enough to favor a different slope here, you might just recover the prior, which is probably what's happening at the high luminosity end. But it has to be consistent with the scatter plots that we see, right? So that's still very, very useful information.
Is radio information for the same access as what was seen in a previous course?
Yeah, it's essentially the same model. Yeah.
But sources are same sources.
Oh, sources are same sources. Most of the sources are not the same. So it turns out, if you look in the radio, if you do a radio survey, and then you go out and do an X-ray survey, you tend to select different kinds of black holes. There's like radio mode accretion and X-ray mode accretion, like very roughly speaking. And they have different luminosity functions. So it's not always a one-to-one match if you look in different wavelengths. Yeah, but that's a great point. Yeah, some of them do have both radio and X-ray detections, which is what's shown on this plot. So this is the radio luminosity of our sources and the X-ray luminosity of our sources, plus the black hole mass. And this is because this is what's called the fundamental plane of black hole activity. And so it turns out like the radio luminosity and X-ray luminosity are kind of correlated, but if you fold in the black hole mass, then they fall along this plane here. Kind of empirically driven. Yeah, what we found is that for the several detections that we had that were in VLA and X-ray, they were at least consistent with this plane within the large scatter, which are our black symbols there. And the magenta points are other low mass black holes from Kai and Viltekin's 2019 paper. So the scatter is large, but at least gives you some idea. So there aren't many of them that are detected in both. But if you did a deeper radio survey, I expect you'd find a lot more. All right, and so then with an eye toward the LSST observatory, I thought, well, could you do this with detections from optical variability? And so this was motivated by, and I should mention Vivian Baldassare, who's the co-author on this work. She kind of started this business of looking for the stochastic variability in very low mass dwarf galaxies in SDSS. And you can see this is a very convincing looking dwarf galaxy with quite long duration variability. And if we assume this variability is coming from an AGN, and there are other things that can produce variability kind of like this, like luminous blue variable stars and other things. But those are quite rare. So if you assume that a lot of these are coming, most of these are coming from indeed a black hole, then you can do a similar thing where we've plotted an estimate of the R band optical luminosity against stellar mass. And we use this kind of sketchy, it's cut off here, but there's a relation between, we assume basically the amplitude of variations that you detect is what's tracing what's tracing the luminosity of the AGN there. And again, you let this power law distribution be a free parameter, and at a certain sensitivity of your light curve, based on the error bars in your light curve, you can no longer detect an AGN of a given luminosity. And that's how you can calculate the upper limits from the error bar of your light curve. And that depends on, the magnitude that you're looking at. Yes, Jeff.
Yeah, I'm not sure when a good time to interrupt with this is, but my issue has to do with the uncertainties connected with the detection, the observational detection. You've mentioned various possible other sources of variability or so on. Can you kind of step back and explain the big picture as what how you think the uncertainties in the detection, the observational detection process, how they affect this whole analysis?
Yeah, sure, happy to. For the variability in particular?
But yeah, that's what comes to mind. I mean, there are lots of ways that variability can be present without black holes, or I don't know how many, but yeah, I'm just wondering in general how many false positives there are going to be in these surveys.
Yeah, it's a very good point. I think I don't have, like a clear number for you, to be honest. All we've done here is said, okay, if we assume these are all AGNs, is that consistent with like a power law luminosity function? That's pretty much as good as we can do for this work. But yeah, taking a step back, in my opinion, the variability detections are quite robust in the sense that, I do believe that the detections are seeing real variability, not just like noise from the instrument.
Yeah, sure.
Because of the stochasticity, right? The correlated noise in them. But yeah, there's been, there's one source in this catalog, just to give you a concrete example, that is actually called the Kinman dwarf galaxy. It's a very interesting dwarf galaxy. It has a luminous blue variable star in the center of it. And the variability looks very stochastic, right? Because it's like a Eta car kind of thing. Some stellar wind interacting with a dense circumstellar medium, and that gives you similar stochastic variability. So, but we know that's the case for this particular object because like the spectral features look more like an LBV star than an AGN.
Sorry, you're saying a single star contributes enough to make the total luminosity look like it's varying?
Yeah, crazy, right? Yes, because it's close enough.
Wow.
It's particular galaxy is like a few megaparsecs away or something. I forget the exact number. Yeah. And they're luminous enough to be, yeah. Some of them are like, and then there's like, type 2N supernovae, like you would catch, if you didn't catch the main flare, maybe you'd see that late duration interaction with the circumstellar medium or these supernovae. Yeah, certainly those could be contaminants, but I don't think we have a good handle on what the rates of those things are. Yeah, so, and I don't know if Vivian has done like a complete spectroscopic follow-up of all of these lower mass ones. But certainly some of them have other evidence for AGNs, like from AGN looking broad lines or narrow line ratios. But as you get to lower and lower masses, those things become less effective. So yeah, it's a great point. I think it's unclear.
So it sounds like there's no simple way to try to quantify this. I mean, introduce some assumed false detection rate or something. Could your analysis be done in a sort of parametric study of that kind of parameter?
Yeah, great question. I don't think it would be easy. Yeah, I think all we can say is, are the detections consistent with like an AGN like power law scatter in luminosity? And you could try to fold in, like if you knew the rates of these like LBV stars or other things that are non-AGNs, of course you can try to fold that into your calculation, but I think it's too uncertain to attempt to do that. At least I did not attempt to do it with this data set. Yeah.
Okay,
But
sorry if I interrupted, but yeah.
oh, please, great. Thanks for that. Yeah, thanks for that.
So if I can follow
Yes.
up on that for a second. So people here can't see it, but the coefficient in front of that is
Yeah.
minus 3.4,
Yeah,
which is very steep.
it is very steep. Yeah.
So it seems like you can, so for large luminosities, AGN luminosities, if you can establish the slope and just extrapolate it down, you should be able to tell if, how much of a bad fit it is at.
Exactly. Yeah. And is that consistent with the And that
That-
equation has luminosity in it, right? So then you have some distribution. Is that consistent with the AGN luminosity function? At
Right.
least a reasonable interpretation of it. And that's what we tried to do. And yeah, it seems reasonable. Like it's hard to measure the luminosity function and harder to measure it in optical, right? Because you have contamination from stars in the galaxy. But you know, I wouldn't put too much stock into this, but at least you get a smooth looking power law-ish thing. That's that was something. Yeah, I think there's another question.
Anita,
See.
go ahead.
Yeah, I have a question. So your hurdle model, it reminds me about the approach which Gwen Eddy took, the hurdle model for the globular clusters, where they were counting the globular cluster in a certain volume and trying to get the numbers. And in that case, they used the hurdle model and they were getting the uncertainties and probabilities of the numbers at the lower luminosity limits. So I was wondering if you know this work. This is new. This is like 2022, I think, paper by Gwen. But they were not calculating the luminosity functions. They were looking at the numbers of possible globular clusters in outer galaxies, not not our galaxy, but the other galaxies. And there was a way, I don't recall right now, but there was a way to calculate probabilities. And when you looked at these lower tails in their distributions, there was a nice approximations. So you get large numbers, but you get this kind of uncertainty. That's what Jeff was referring to, I guess, as well.
Ah, okay. Wow, I have not seen this. I will look this up after. Thank you.
Yeah, and they have the whole Bayesian model for the fitting of this data. So maybe that's also applicable. I mean, it would be nice to get this connection and maybe get this, the uncertainties at this faint ends on the occupation fraction.
Yeah, great. I think there are many applications to these binomial hurdle models in astronomy. I've also seen another paper where they looked at, for example, the M sigma correlations, the relation between the black hole mass and the stellar velocity dispersion of the galaxy, which is a nice linear relation, but some of those you have some upper limits, right, where you cannot measure the stellar velocity dispersion or the black hole mass. I don't know which, but you have some limits on there, right? But you don't know if there's a black hole there or not. So you kind of need to do it technically, to do the regression correctly. You kind of need to incorporate that into that.
Right.
Yeah, and actually, if you look back at the Nuker paper, they kind of did this in a less sophisticated way, but they do have a delta, Dirac delta function in there for the fact that there may not be a black hole in there, and that would not be dynamic. That we would not see a dynamical detection of. So yeah, thanks for bringing that to my attention. Yeah, you do have to be very careful about how you do the integration over the unknown data. But yeah, I think they have many applications. Great. All right, so I will try to wrap up just by, we looked at this plot earlier in your office. So just to horrify you or impress you, I don't know which, you can combine all of these three data sets at the likelihood level, because we know there should be, well, we're assuming there should be a universal occupation fraction. Okay, but if you look in the radio, if you look in the X-ray, or you look in the optical, the luminosity functions are different in their slopes. And even this black hole mass stellar mass relation is probably a bit different. So you can let those parameters vary, and we have horrifying number of parameters. But at least this gives you a formal way to combine all the information that we have together. And when you do that, you can then back out the occupation fraction for our complete data set. In this case, it's essentially just recovering the results from our variability in X-ray data, because those were more sensitive than the radio data that we used. But stay tuned for additional radio data. And you can then combine this, take these combined constraints, and so this is the occupation fraction, again, they're limits still, versus stellar mass, and you can compare this to other observational constraints. So so I apologize for the busy plot, but just to point out a couple interesting things. So the X-ray, purplish X-ray detections are from the AMUSE survey. And the way it's plotted is a bit confusing. This is also a limit, so it's consistent with our result. A lot of people got confused, by the way, in the literature, thinking this was a detection and not a limit. And so people have like, oh, we matched our model very well, but actually it's just a limit, so whatever. Because they put a prior here. If you really carefully read the paper, you'll see. And we double checked it, so yeah. This green shaded line here are detections of nuclear star clusters in field galaxies in the local volume, and then in the Virgo cluster. And so you can use the nuclear star cluster detection rates as a proxy for the whether there's a black hole there or not. And if you believe that they backed out this nuclear star cluster, rate correctly and accounted for the same kind of similar selection effects that we've had to deal with, and I don't know for sure that that's the case, but if you take this result, then it implies that there are many more black holes than nuclear star clusters. So that's an interesting result. Again, needs further observational confirmation. Okay. All right. And I will try to wrap up here. Okay, this is the motivation for the exact form of the sigmoid function that we assumed for the occupation fraction. Turns out it can be calculated by halo merger statistics. So the number of halos that merged to create a redshift 0 halo. And then you can convert that halo mass to galaxy stellar mass, and then calculate how many mergers, a given halo or a given galaxy at a stellar mass has had on average statistically, and plug that into the binomial formula. And turns out you actually recover similar looking curves here. So there is some, physical motivation for this logistic regression, okay? And if you make some very oversimplified assumptions, like what's the probability that a halo at very high redshift was seeded above a certain halo mass, and you assume that that's independent of halo mass after that, and you put in some fudge factor for those number of black holes that actually grow, to fall on this black hole mass stellar mass relation and so on, then you can say something quantitative about the seeding probability in high redshift halos. Very uncertain. I'm not claiming this is like an astrophysical quantity that you should go and get constraints on, but I think it's a nice conceptual and simple analytic way to think about it. And you probably want to calibrate all this stuff to numerical simulations. Okay. Okay, and so that's what people have actually started to do. So this is really cool work from Klot Bomick, who's doing some really interesting work with, this is all based on the illustrious TNG simulation, I believe. And he has some scheme to it's like a Russian doll, you use a higher and higher resolution simulation so you can resolve seeding on smaller scales and then track it out, over the entire cosmic time. And don't ask me about the details of all of these seeding models that he's put in, but these are essentially different heavy seeding models, but cranking up certain parameters that you need in order to form a seed. So it's kind of a proxy for the seeding efficiency at high redshift. And it has some constraining powers. We're actually able to rule out some of these more pessimistic models using our observations. So, okay, we can also then back out the black hole mass function, and stop me if I'm going over, by multiplying the occupation fraction with the galaxy stellar mass function, and then you can get these nice constraints here. Yeah, then I think I'll stop just by saying that Yep, I'm currently doing a VLA filler program to try to do much deeper, randomly targeting like 10 megaparsec galaxies to try to do an unbiased survey, kind of volume limited survey, to try to confirm or measure the occupation fraction in the radio a bit better. And then also I'd be curious to hear other people's suggestions or ideas. Like a lot of people have tried to go at this from X-ray stacking. I know there are ways you can maybe infer the luminosity function from stacks. And would that give us better statistics? I don't know. But yeah, thank you for your attention. I think I'll leave it there.
From online. We lost half the people, but there's still some hardcore.
Okay,
people,
that's
so-
good.
So
There's still some people left.
About the slide you were showing with the results that you said were from illustrates. So I assume that those are not upper limit, or not limits, but from the yeah.
Lines, yeah.
Yeah, so if those are not limits, is the way to think about the limits on the occupation fraction that they are lower and to the right? Like that the occupation fraction
Yeah.
that you would calculate from any one of these simulations is somewhat
Mhm.
higher than the limits that you have been showing?
Okay, so my limits here are now shown in this purple.
Okay.
So anything within here is allowed if you believe my paper. This gray, you can ignore this, is from the old work. So my paper is more constrained. So if you believe this, then all of these models that are outside of this magenta shaded region are not allowed by the data, ruled out.
Okay.
Yeah. And you can do a more careful, you know, if you want credible interval calculation to see. But these are for sure ruled out by, like, this is like 2 sigma ruled out, you know, this is probably like more than 5 sigma ruled out. But it's all degenerate with the assumptions you make. So I'm sure you can still have heavy seeding and tweak enough things to get it to match the observations. So it's not like my work is like a direct constraint on like seeding theories, but it's a constraint that's important that the theorists have to match. Yeah. It's hopefully somewhat useful.
Yeah.
Yeah.
Yeah, that definitely answers the question.
Great. Yeah.
Any other questions? If not, we are almost exactly an hour.
Wow, fantastic.
So
I did not plan that. That's just my instinct. Yeah. Thanks for the great questions.
as predicted, you know, prepare for half an hour of questions.
Yes. That's much better than just talking for an hour. So, yeah.
Okay, so I'm going to turn off the recording and one